All right, I'm going to do this first example using the formal method. So I'm going to start by drawing a free body diagram for each object. So the first one will be the object, capital M. The mass is given as 3 kilograms. It's got gravity down. It's got normal up. And they're going to be equal in magnitude. Those are the only vertical forces, so they have to be equal in magnitude because the object is not moving or accelerating vertically. Then it's also got the tension. So the tension is going to the right. Maybe I'll just use T, capital T, for short. All right, now the other object, I'll draw that free body diagram on the right side of the page. So the mass is a different mass. I'll use lowercase m. It's given as 2 kilograms. So this object that's kind of hanging down from that string there over the pulley, it's got its own gravity. Oops. And it does not have a normal force because it's not resting on any kind of surface or touching any kind of surface. But it does have the string pointing upwards. And I drew them different sizes because this is going to accelerate downwards. I know that for sure because the table is frictionless. There's nothing to kind of resist these objects from moving with the capital M box sliding to the right and the lowercase m box going downwards. So it will accelerate downwards. Another reason why I know they accelerate for sure is if I look at the free body diagram for capital M, the forces are not balanced. The vertical forces are, but there's a tension to the right, and there's nothing balancing out that tension. So for sure, it's going to accelerate. So these forces are not going to be balanced. All right. The next step would be to write equations for both objects, and I want to make sure that I've got tension in both equations because they're sharing the same rope. They're tied to the same rope. That rope is going to have the same tension all throughout it. So whatever tension I get for one of these objects, it's going to be the same magnitude of tension for the other object. They're pointing in different directions, but the magnitude's going to be the same. So I'll start with the one I did in black. So what formula can I write that has tension in it? Well, that would simply be Newton's second law. So if I write the net force of this object on the left, well, gravity and normal cancel out, so the net force is just the one force. It's just the tension. So there is a formula with tension in it. Furthermore, I can change the net force to MA, and that'll equal to the tension. And now what I'm going to do is I'm going to actually, so those vectors are equal, but if the vectors are equal, then their magnitudes are going to be equal as well. So I'm going to throw magnitude bars there, and maybe you'll see why in a couple minutes. So now I'm going to focus on my blue free body diagram there for the hanging mass. So I want to write a formula for that. I want to make sure tension is part of this formula too. Well, this one there's not much choice. There's only vertical forces. So I'm going to write a statement dealing with the vertical forces. So I'm going to do it in terms of magnitude as well, so that I can use the magnitude of tension that I got previously. All right, so the magnitude of this net force. So gravity is bigger than tension. So the magnitude of the net force is going to be the magnitude of gravity minus the magnitude of the tension. So that is a formula I can write for the other block. Okay, so I can change this F net to MA as well. I see a mistake on the black side. I'm going to have to go fix that. FG is force of gravity. I can change that to mg. And I'll keep tension as tension. Okay, so the mistake I made on the black free body diagram is that I wrote a lowercase m for the mass after Newton's second law. These are two blocks of different masses, so we better make sure we keep them distinct. So better write capital M. Okay, so what I have are two equations. I'll just number them, 1 and 2. In two unknowns, the masses are known. Okay, they're listed over here, so those are known things. So the only two variables I do not know are the acceleration and the tension. And those two variables are actually shared variables between both objects. I already talked about how the tension is going to be the same because it's the same rope. But the accelerations are also going to be the same because these objects are going to move together. The reason why the block on the table moves to the right is because it's being basically pulled by the other block. So they're intimately connected. They're going to move at the exact same acceleration. So two equations and two unknowns, and we just use either substitution or elimination or Wolfram alpha to solve. The question asks what will happen. So I guess what we can calculate the acceleration and we can calculate the tension, but the question doesn't sound like it's asking for the tension. By what will happen, they're probably asking how's it going to move. So I'll solve for the acceleration. So what I'll do is I'll take this expression, which is equal to the tension, and I'm going to substitute it into the other equation for where I see tension. So underneath that, I will write what I'm left with. So equation 2 is going to be rewritten. And it'll be rewritten as follows. It will change that tension to capital M times the acceleration. And that is an equation I can solve for the acceleration. Okay, so I got to get acceleration by itself. There are two terms that have acceleration in it, so I'm going to bring them both to the left side. So I will move that negative capital MA, move that to the left side. It becomes plus capital M A. So that's just collecting like terms. So I can common factor out the acceleration. And then I can divide both sides by m plus m. In that, now I'll just fill in the values. So lowercase m is 2, g is 9.8, and then m plus m 2 plus 3, and I'll figure that out in the calculator. Okay, so that's to 2 sig figs, that is going to 3.9 meters per second squared. So the answer to what will happen is the blocks will move, or the blocks will accelerate at 3.9 meters per second squared. The directions are different for the two blocks. So the big block that'll be to the right, and for the little block that'll be down, but they have the same magnitude of 3.9 meters per second squared. So that's the formal method. The informal method, I'm actually just going to highlight. That last step right there. The informal method basically jumps right to that step. Like I practically start there almost. Maybe 1 or 2 steps before that, but it's a lot quicker. So the informal method would be to analyze this whole thing as a system. Method 2. We analyze the whole thing as a system. A system with a total mass of 5 kg. And I kind of take a look at the situation and I think, what are the forces that would drive it to go forwards? I would have to define a forwards direction. I'd draw something like this. So maybe when the pulley is spinning clockwise, that's going to be called forwards. So what forces are driving that system forward? Well, that would simply be the gravity of the little block. What's holding the system backwards? It would actually be nothing because there's no friction. So I would say that my F net for the system would just be mg. That's the only force driving it. So then when I do Newton's second law, I'll do acceleration is net force over mass. So it would be mg over 5 kilograms, which is exactly what we got basically in the very final step of the formal method. Okay, so I think the next example I may try to just do the informal method, and maybe I'll go back and forth between the two methods for all these examples.